Yeah, so then I guess maybe for the benefit of the recording, hello everyone, Alex again. Sort of last minute decided I would try to make use of the time slot that maybe people had set aside and stuff, and kind of keep the momentum going for Brainiversity and stuff. And I had sort of additional slides left over, and I had promised to kind of talk about some additional stuff. So I thought I'd sort of kind of wing that today and talk about some of the things I kind of wanted to talk about but didn't get to. But fair warning, not going to be as kind of polished potentially. So feel free, I guess, like here's an invitation to make this much more interactive, right? So please, ask questions and talk and things like that, and let's try and have fun. So the slides are actually the same. I'm just I added to the end of the slide deck. So here are the Go links again: Go Brainiversity Info Theory. Go Brainiversity Info Theory problem set. I've actually nearly finished. I'm working on the last solution. I have the solutions kind of ready, and maybe later today or the next couple days, I'll give them to Penang to upload to the thing. I don't know. Hopefully people have been taking a look at that. I think it's kind of interesting. I admit it was more work than I anticipated, even for me to create the solutions. But the point, I do think that they're interesting things, and I'm sort of having fun myself, even sort of thinking through them. So hopefully they're there if you wanted to kind of dive deeper, but I will put up the problem set solutions. And then, there we go. So maybe one thing to start with, and maybe this is good to kind of like just kind of limp in as maybe we give other people some time to come in. There's actually an example that I kind of wanted to work through last time that I didn't get around to, and I think it's kind of neat and has some implications for the kinds of things that we do. So thinking about sort of weight of evidence and our belief-o-meter again, let's say I wanted to try to identify a single person in the United States. How much evidence does that take? Now, the US population, I think, is like 320 million, something like that. So the odds like that I were to guess correctly your identity, if you were just some anonymous person or something on the internet or using my website, are sort of 1 in 320 million. In our sort of deciband scale, that corresponds to negative 85 decibands that I kind of can guess your identity correctly. But I can collect information, right? And I guess like, what sort of information might I collect? Well, one thing I might ask is what your birthday is, right? I might have a little form that asks for your birth date, not even the year. Let's just start with the birth date. You tell me that your birth date, mine is February 4th. When I tell you that my birth date is February 4th, I'm giving you some information, and I'm giving you sort of 1 in 365. The odds, of selecting that one day are 1 in 365. On the deciband scale, that corresponds to 26 decibands. So I can kind of like knock that off, right? I've accumulated 26 decibands on a hypothesis that I started sort of at negative 85. I kind of move up the meter a little bit. Let's do the next thing. What if I told you my age? Now, my age, I don't know, but let's take a rough estimate. Like, let's assume, the lifespan in the United States is something like 63 years. So if we assume that people are uniformly distributed in age over 63 years, then that would give us like 18 decibands. If you actually look up the actuarial tables for the United States and do like P log P for the fractions of people in the United States that are every age, you actually end up getting 19 decibands. So close, but to our kind of rough estimate. But that's another 19 decibands of evidence that I might collect. I can put that sort of on the list. So now this is like birth date and year. Let's say I add your zip code. How much information does that tell me? Well, there are probably about 10,000 or 100,000 zip codes, right? It's a 5-digit number. 1, 2, 3, 4, 5. Yep, it's a 5-digit number. So if they were uniform amongst all possible zip codes, that would be 50 decibands, right? Because 10 to the 5, log base 10 gives us 5 times 10 gives us 50. 50 decibands if we had a uniform thing amongst 10 to the 100,000 zip codes. In actuality, it seems like there's only about 43,000 zip codes in use. Log 10 log 10 of that is 46 decibands. Again, if you kind of look up the Postal Service and you look at the populations and all the zip codes of the United States and do P log P and sum the whole thing up, you get something like 41.6 decibands. Add that to the list. Yeah.
Alex, quick question. Are you doing P log P or just log of 10 log P?
Oh, sorry. Yeah. So to get the 41.6 decibands, I looked up, a source that had the population in every zip code. I compute those, I turn those into probabilities like fractions. And then what I'm computing is 10 log 10 of that fraction summed over all the zip codes. So it's, speaking fast, I'm going to say that's like P log P summed over all P, but it's, you muted yourself, but I think you were agreeing.
Oh, sorry, 10 log 10 of sum or P log P, basically.
Yeah. The sum of 10 log 10 of, the sum over all zip codes of the fraction in that zip code, 10 log 10 of the fraction in that zip code, in order to get the decimands. And here we get 41.6. But I guess to give you some intuition, that's relatively close to this just rough estimate if we say it's 100,000 or something. Okay, add that to the list. And now what if I tell you my sort of sex or my gender? Most people identify as male or female. It's roughly binary, and so that's roughly 3 decimands. You add all these things up, and what you actually get is if you started at negative 85 decibands, you add 26, then add 19, then add 41.6, then add 3, you're actually 5 decibands to the right. So we went from the chance that the belief that you had in this hypothesis being at negative 85, and if all I do is ask your birth date and year, your zip code, and your sex, now I'm at 5 decibands on the positive end. I actually have accumulated 5 decibands in favor of the hypothesis that I can identify you uniquely. And it turns out that this actually kind of roughly aligns with reality. There's a famous paper from 2000 by Sweeney. She showed that you can actually do this. 87% of Americans are uniquely identified by just their date of birth, age, and zip code, and gender. So, you don't really think about it when the website asks for like your birth date for age verification or something, but like that combined with just your zip code, like your IP is probably similar, is sort of usually enough to uniquely identify who you are. So I don't know. I thought that was an interesting example. Okay. In terms of like some content, so one thing I didn't get to say, but I sort of wanted to is, so mutual information, we talked about mutual information. I guess to remind you, mutual information you can think of as the relative entropy between the joint distribution and the product of marginals, or you can think about it as just intuitively like the amount of information you reveal about one variable when you observe the other. And the question then becomes like, what does this mean for things like continuous or invertible functions? A lot of people talk about things like trying to measure the mutual information in the parameters of a neural network or something. And that's, often we assume or we model it as a real valued number. What does sort of mutual information mean for things like that? And the first thing I want to emphasize is if you had an invertible transformation, like some function G, then the only reasonable definition of the mutual information between a random variable and an invertible transformation of that random variable is infinity. And that, I think, hopefully intuitively makes sense in the sense that a real valued number, right, the abstract notion of a real valued number is, a number with an infinite decimal expansion. It takes an infinite amount of information to ascertain a real value. That's just sort of like the, Now, if what I do is I tell you the value of some perfectly invertible function, if I tell you g of x, how much does that tell you about what x is? Well, if the function is invertible, it tells you everything. It tells you everything that you would ever need to know, because all you do is you compute the inverse, g inverse of g of x, and that tells you x. And so for real valued entities, if you observe some invertible function of that real value, it tells you everything you would ever need to know about that real value. And as a continuous entity, there's sort of an infinite amount of information there. But that's not to say that mutual information involving any continuous random variable has to be infinite. And here's a simple example that I think also sort of intuitively makes sense. The mutual information between a real valued random variable, let's say uniform between -1 and 1, and the sign of that random variable is exactly 1 bit. Even though we could imagine this x as being a continuous real valued thing from -1 to 1. If I tell you the sign of it, what do I tell you? I actually tell you 1 bit. I mean, literally in terms of, kind of floating point representations, I'm telling you the sign bit of the float, right? There's one less question that you need to ask in order to ascertain what the value is, namely whether it's greater than or less than 0. I've given you that much information about the value, right? If I had a uniform real valued random variable from -1 to 1, and I tell you it's sign, I've cut the possible search space in half. Even though that space is like a continuum and there's an infinite amount of information left to resolve a value, it's half as large as it was to begin with. And so, and the mutual information in this case is legitimately finite, and it's 1 bit. So this is, it can be finite anytime you have a very, you know, a very many-to-one style function, something like a sign or a step function, a rounding function, things like that. If there's a finite number of outcomes that things could have, then you can still get finite mutual informations for continuous real random variables.
Alex, I have a quick question.
Please,
I'm
yeah.
wondering intuitively if the inverse of the first claim is also correct. If you have a continuous random variable and then another one y, and mutual information is infinity, can one say that one is an invertible function of the other, or are there counterexamples?
You know, that is a great question. I don't know the answer. Intuitively, it feels like to me that there should exist some transformation. I mean, in some sense, like, I mean, in so much as you could, okay, well, let me say it this way. There are lots of examples I think I can come up with for which mutual information is like infinite or nearly infinite, but for which that information can never be practically made use of. So like hashing, like cryptographically secure hashing. If I take a random variable or some, you know, continuous real valued thing and I sent it through some cryptographically secure hashing function, that's invertible. Or, well, you could imagine a cryptographically secure invertible function.
Yeah.
And that should reveal a tremendous amount of information about what the value is, but that information might not be readily accessible or even like computationally practical to, you know, extract.
Yeah.
So this is actually like honestly a, you know, whether it's a curse or a benefit of mutual information doesn't have any notion of sort of computational complexity built into it. All it is a measure of how much information does exist. It doesn't tell you whether or not that information can be practically accessed or computationally, you know, cheaply or in any like, you know, finite time or anything like that.
Yeah.
So I don't know if that answers the question, but that's the best answer I got.
No, thanks.
Yeah.
Another quick question. So for
Yeah, please.
the top equality, I can see how you'd get it if you look at like mutual information as the KL between the true joint distribution and like the assumed product distribution. But if you say that like the mutual information is the entropy of X minus the entropy of X given G of X. So the entropy of X given G of X should just be 0, right? Because it's deterministic. So then that would suggest that the mutual information should just be the entropy of X, which doesn't necessarily have to be infinity, right?
Well, so I guess that's the thing, right? So continuous entropies are honestly pretty meaningless. And that there's a real sense in which the entropy of a real valued thing is infinity, because there's an infinite amount of you know, information or you know, digits in the decimal expansion that you need to specify in order to specify the value. That's not to say that the continuous entropy, if you were to compute it, is you know, that's almost never infinite. But that continuous entropy, maybe say it this way: the entropy decomposition of mutual information you should not take to be true for continuous valued quantities, but the mutual information is well defined because it is sort of dimensionally consistent. It's the log ratio. It is the log of the ratio of densities. It is well defined and is a mathematically sort of correct thing to talk about, even for continuous random variables. Continuous entropy is sort of not.
So does the KL definition work in both cases?
Yes, and
So
we had. I don't really want to go back like you know, 100 slides in the thing, but I think the way to think about it is, you know, really for a continuous random variable, we don't have a probability distribution. We have a density, right? So what you're giving is like P of X dx. You're giving the probability that it's found in some small region. If you had some Q of X dx and you take their ratio, then the dx is canceled. And so like the formula is correct and the formula works whether or not P of X and Q of X are probability distributions or their densities. Like the formula kind of remains unchanged. That like breaks down for the continuous entropy. And that's sort of why that quantity is sort of weird. Now, I talked about it like basically, okay, my advice is, don't use continuous entropy. Now, I say that, but like lots of people do. And what you need to be kind of very cognizant of is anytime you use the only way to kind of make continuous entropy make sense is to really think about it as a KL divergence with respect to some like improperly defined density on the space. Like you have to be very explicit about the units that you're using to define things. And that's a slightly different quantity, like like ontologically than the thing that people think that they're talking about, but you'll get the same numerical numbers that people put in their papers. And that quantity is well-defined and reparameterization independent and stuff like that. Because, so anyway, the take-home lesson is be very sort of, your ears should perk up anytime you hear people talking about continuous entropies, because they really are a more subtle thing. But KLs are perfectly fine. Mutual informations are perfectly fine. Anything that involves log ratios of densities are perfectly fine. Once you try to split that log density ratio into the two components, then it really matters whether that thing's supposed to be a density or a distribution. And you should be aware of that.
Awesome. Thanks.
Yep. Okay. I don't know if this is going to go well, but I wanted to try to give another interpretation for mutual information. And at some part in my head, I think about it as like counting the effective number of tubes between two random variables. And that sounds weird, and it's probably going to sound weird, but I can try to give you this notion. So where is this coming from? I mean, when we talked about the asymptotic equipartition theorem, the one of the interpretations I wanted you to leave with in terms of entropy was that it's a measure of the sort of effective number of typical. When you draw a lot of samples from a random variable, it behaves as if it was a uniform from a population of a smaller size. The entropy was the thing that told you sort of the effective number of different typical sequences that you could observe. If you remember our coin flipping example, I imagined a biased coin that had a bias of 11%. The entropy in that case was half a bit. And so if we flip the thing 100 times, even though there are 2 to the 100 possible binary sequences that are 100 bits long, if I flipped a biased coin with a bias of 0.1, then the number of typical sequences, meaning sequences that were within like sort of epsilon of the entropy that you would expect, are only 2 to the 50. And 2 to the 50 sounds like a big number, but it's nothing compared to 2 to the 100. That 50 is telling us that, in the 100 flips, that biased coin really sort of behaved as if it was 100 flips of a thing that only has a half of a state rather than having one state. The entropy being half of a bit tells you that there was sort of like half of a possible value that each flip could contribute as the number of flips goes large. So if we think about two random variables, x and y, if we just look at the y for a second, we could ask the same question. Just given some random variable y, like how many different values can the thing take in lots of samples? And the answer should be something like 2 to the n times h, where h is the entropy of that random variable if I had n flips. And you could imagine this sort of tiling the space into small, number of buckets or balls or something. Now, if what I do is I observe some value of x, and I only look at the values of y that kind of result from that bucket. So like here, I've got some, set of typical sequences in x, and I look at where that maps to in y, right? If I observe x and there's some relationship between these two things, there's going to be some subregion in the y space that corresponds to the possible values that this thing could take if I knew what x was, if I only looked at the region that came from, mapping some small region in the x space. And how many sort of independent things are there that live in there? Well, that's going to be 2 to the n times the entropy of the things in there. But the entropy in the things in there is the entropy of y, given that I know what the value that x was. If I know that x was little x, then the remaining entropy is going to be the sort of number of possible values that y is allowed to take left. And the mutual information is just the ratio between those two things averaged over the whole space. Because if I look at 2 to the n times h, y, so the number of possible different things in all of y, and I divide it by 2 to the n h of y given x, but I do this over all possible x's, the ratio of the two, exponents is just their difference. And that was another way we talked about what mutual information was. It's a difference in the entropies. It's the reduction in the entropy. Mutual information between x and y is h of y minus h of y given x. And so you can think about mutual information, that number. It's saying that as I draw lots of joint samples from these two random variables, amongst all possible kind of pairs that could show up, the number of independent typical pairs grows like the mutual information. It's in some sense a measure of how many different tubes exist, how many independent distinguishable tubes exist between x and y as I draw many samples from them. And yeah, I don't know if that helps for anything. I wanted to, so I didn't have time, but I'll invite you, I think you can try to make this analogy richer and make more sense to yourself if you think about trying to compute the mutual information between, some random variable, and if I cluster the random variable into groups. And you'll sort of discover that the mutual information corresponds to the sort of number of clusters that you try to cluster the random variable into. And I was originally going to kind of work through that, but I didn't manage to finish that sequence. Okay, in terms of the last fact that I wanted to convey that I don't think I did a good job of conveying, and then we'll move on to talking more about modeling and learning and VAEs and stuff like that, was this sort of fact of the data processing inequality. And really at its core, it's a pretty obvious statement. Information cannot be created, it can only be destroyed. That's the sort of way to, that's the way it should live in your head. That's, a thing, almost like a kind of information theoretic second law, something that you can stick in. Information can't be created, it can only be destroyed. Practically speaking, what this means, and mathematically the statement is, if I have 3 random variables that form a Markov chain, and the Markov chain is just sort of a fancy way of saying that I take, some random variable x and I process it, or I do some transformation to it to get z, potentially adding noise. And then I transform the z's in order to get the y's, meaning that the fact that this is a Markov chain means that if I observe z, then x and y are independent, right? Because there's no sort of, one way to achieve this was if there was no causal relationship between x and y except through z. Then anytime I freeze the z to be some value, then the x and y's are independent, and I sort of don't learn about one given the other beyond any of the information I observed in the z itself. If you have a Markov chain, so if you really have a thing where I kind of take an x, I process it and get a z, and then I take the z and I process it and I observe the y, the mathematical statement about the data processing inequality is telling you that the mutual information between x and y is always less than or equal to the mutual information between x and z. In words, what does that mean? If I took a thing and I process it to get z, there's going to be some mutual information there. There's so much information that's preserved in that process. If I then go and do more to z, and I process it some more to get a y, there has to be less information, or an equal amount, but less than or equal to the amount of information that was present in the z. Any processing that I do, any transformations that I make to a random variable, anytime I kind of do something to it, potentially adding noise, I can only ever decrease the amount of information that is retained about some earlier part in this process. I can never make it go up. It can only ever go down. And in some sense, this maybe is already clear. We saw that if I had an invertible transformation, mutual information is sort of infinite. If I add any amount of noise, it's finite. But that's true for any step in this chain. If I ever add any noise as any part of the intermediate processing, that's only ever going to make mutual informations kind of go down. It's only going to destroy information about the sort of original input to this chain. It can never make it go up. And this is a very crucial result, and it kind of powers a lot. It's a good thing to know. I mean, it really is, I think, sort of as simple as it sounds. You can kind of show this graphically, I think, and I wanted to kind of work through this just to get some more practice with these sort of Venn diagram things. So imagine we have a random variable x. It's sort of this whole blue ball, a random variable y, this whole red ball, some random variable z, this whole green ball. The fact that we have a Markov chain means that x and y are independent if we observe z. In terms of mutual informations, that means the information you learn about x, if you observe y, is 0, provided you've already seen z. So the conditional mutual information between x and y given z has to be 0. These two are equivalent conditions. This mutual information being 0 is the same as saying that this thing follows this Markov chain. What does that mean in terms of our diagram? Well, where is this region? The way to read these diagrams, right, is think about them as sort of set intersections and stuff. So the mutual information between x and y is the intersection between x and y. It'd be this whole region here. If we condition on z, that means we look at the region exterior to the z. And so the mutual information between x and y conditioned on z is this little sort of triangle region here. Being a Markov chain means that that region is 0. So I'm just going to move the diagrams that region doesn't exist.
Can I ask a quick question? Why is it one exterior to z?
I mean, that's, I guess, how, I don't know, that's how these diagrams work. I guess, like, you should think about it as, let's just think about two random variables for a second, just x and y. The entropy of x, we're kind of representing in the Venn diagram as the whole area of the blue circle. If I conditioned on y, that means let's say I know the value that y takes. How much information is left? Well, I remove all of its intersection with y. The only stuff that's remaining is the stuff exterior to the y region. That's the remaining noise in the process. I guess imagine the extreme case if x was an enclave of y, if it was entirely contained in y. Once I conditioned on y, the entropy is 0. That would be as if x was just a deterministic function of y.
Yeah, thanks.
Yep. Okay, so then enforcing the Markov chain condition is just sort of modifying this diagram so that that little region vanishes. And now we can just sort of like, let's just see if we can read off the data processing inequality in the Venn diagram and see if it's true. So we just need to identify these two regions. What is the mutual information between x and y? Well, it's the intersection of x and y. The intersection of x and y is everything that's both blue and red. That's this region right here. And what's the intersection between x and z? It's the intersection between x and z. It's this whole region here. And the data processing inequality is just saying that this region has to be less than or equal to that region. And hopefully it's sort of visually clear that that's true. And that sort of has to be true. Okay. I don't really know if I want to say this. I'll sort of say this, and I'm going to do a bad job of this. I wanted to do a better job. But there's a form of the data processing inequality that holds even at the level of KL divergence, which is more fundamental than the one that holds at the level of mutual information. And what it, perhaps intuitively, I want to tell you what it is. So the statement is that if I have some random variable x, and that random variable might come from two different distributions. I've got some distribution P and I've got some distribution Q. Let's say I draw samples from P and that's my X. I draw samples from Q, that's my X. And now I process it. So I send it through some conditional process. I'll add noise to it. I'll flip it. I'll rotate it 45 degrees, add some jitter noise. I'll add some pulp and pepper noise. I'll do something to it. I'll send it through a channel in order to create a Y. We can ask a question. And the question is, how should, let's say I originally started with some distribution P and some distribution Q for the X's. After I send them through this noisy channel, you know, if I took a sample from X and I send it through the channel, I could write down a distribution of all possible Y's, right? Imagine for a second I were just pushing buttons on my P box, generating X's, and for every one of those X's, I send it through the process, I transform it, I augment it, imagine like an image that I do data augmentation to. I'll get out something. Imagine I do that an infinite amount of times and I generate like a histogram over all possible augmented images. That's some distribution, P of Y, of all possible augmented images if I augment them, drawing them from P of X. I could do the same thing with my Q of X. I've got some other distribution, some other image producing box, some other model. I push the button an infinite amount of times. I augment all of those images. And what I get are augmented, you know, Q images. I'm going to call those Q of Y. The question is, how does the KL divergence, how close can we say anything about how close P of y and Q of y are versus how close P of x and Q of x are? And the answer is always, or greater than or equal to, after we transform these things through any process, they have to be closer together. That's the form of the data processing inequality at the level of KLs. If I had any model of images, any sort of GAN or anything that produces images, and any other model of images, they might have some divergence between them. There might be some KL divergence, some degree expected weight of evidence that I could collect to distinguish between the two models. If I do anything to those images that involves any amount of noise, I add some Gaussian noise, I do some kind of data augmentation to them, it has to be harder to distinguish between the two models than it was originally. And this hopefully makes some intuitive sense. If I inject any noise to the process, it's just going to get harder to be able to distinguish things than if I didn't inject any noise. But this is a sort of very fundamental property of KL divergences. Proving the data, one way that you could prove the data processing inequality for mutual information is you could literally take this and then just stick in our definition of mutual information as KL divergences, and you'll kind of get it that way. This works for, yeah.
Sorry, go ahead.
Sorry, a quick question. So S is a KL divergence, right?
Yes, sorry. Yeah.
So is the sign flipped by any chance?
Does the sign flipped? The KL divergence is greater. No. So they're closer together, right? KL being small means that it's hard to distinguish between the two distributions. KL being large means it's easy to distinguish.
Got it.
Yeah.
Okay.
Your KL is there is a sign, but the sign is the difference between KL and entropy. I think you're used to thinking about entropy, and entropy is, large entropy corresponds to large uncertainty, whereas
So KL divergence small means it's harder to distinguish. Okay.
Because KL divergence being 0 means the two distributions are the same. Yeah.
Right.
I also had a quick question. Is the difference between these two KL divergences meaningful in information theory?
Is the difference between these two KL divergences meaningful?
Like, for example, could the difference be, I don't know, the KL divergence of something which depends on the conditional y over x or something like that? I just no.
Yeah, it's an interesting question. I don't know, or if it is, it's eluding me at the moment. I don't know this sort of this difference. Like, it very clearly is a property of the channel, both a property of the channel and the kind of distributions you're sending through the channel. But I can't immediately identify it as like a named thing.
Like, for example, do you know if the equality happens, we can say something about the process? For example, we can say that it's
You can say it's invertible.
Okay.
Yeah, equality happens in the case of invertibility.
All right, thanks.
So this works for any kind of processing, and one form of processing is just marginalization, just throwing out some of the dimensions. If I had some distribution on 2 dimensions, like x and y, a p of x and y and a q of x and y, but then I only observe, let's say, the second dimension, the y's, it has to be harder to distinguish p and q than if I looked at all dimensions. So any marginalization has to decrease the KL divergence. Okay, so that was kind of topics and stuff that I sort of didn't get to. And now what I wanted to do was kind of talk maybe more like philosophically, and maybe even like leading up into variational inference and stuff like that, sort of ways that I think about VAEs and information bottleneck and even like Bayesian inference and stuff like that through the lens of information theory. So this is now we're heading into the stuff where caveat. Anyway, this is my personal kind of views of how these things work, but ones that hopefully now you can appreciate after we talked about things like weight of evidence, KL divergence, and all that stuff. So I guess I don't know if I really wanted to. Yeah, my own personal kind of view of things is our job in machine learning is to try to separate signal from noise, and that is a sort of subjective thing, but entropy is some measure of like noise. This is actually Boltzmann's tombstone. He has carved this fundamental formula from statistical mechanics on his tombstone. Anytime you have data, and like here I've got actually samples from a model that I trained, there's a certain amount of information contained in the process, right? Here is a model that generates things that look like digits. And I happen to know that for this particular model, every sample, I know the exact entropy because I built the generative model, and there's exactly 303 bits total, in every sample. So anytime I hand you one of these images, I'm handing you information. I'm handing you potentially 300 bits of information because I give you this 28 by 28 grayscale image. Amongst all the possible values it could take, this model takes a vanishing fraction of the space of all possible images, and every one of the images that it produces is sort of as distinguishable from one another. It gives you 300 bits worth of information. It sort of answers 303 yes or no questions. But how many of those yes or no questions do you care about? Probably very few of them. Most of those bits have to do with things like whether a particular pixel somewhere in the image is on or off, is black or white. Very few of those 300 bits. Any question that you could ever want to ask given that image has to be contained in those 300 bits. One question you might ask is, which number is the picture a number of, right? What's its class? That only has 10 possible answers. Because it only has 10 possible answers, and because of the way I generated my model, it happens 1/10 of the time. That is only 3 bits in every image. 1% of all of the information contained in that image has anything at all to do with what class it is. Only 1% of all of the information contained in every sample is in any way relevant for the question of what type of number it is. And that is a small fraction of the total amount of information contained in that sample. And this, I argue, is generically true for any data. The picture the way I kind of think about the world is, one of these kind of big Venn diagrams. You've got a whole world of possible entropy. And in this whole possible world of entropy, we'll call it noise. There's some small region in the space that we think is important, that is semantically relevant or meaningful to us, or for some question that we want to ask. And that's a small region, some golden nugget in this large sea of noise. And our job as machine learners is to somehow separate the signal from the noise, sift into this haystack, and pull out the needle. And so what we want are objectives. We want principles for learning. We want, machines that we can train that can basically pull the needle out of that haystack. There's broadly 2 strategies you could do to try to get the needle, right? One strategy is I could just try to make a hay slurper. I could just try to build a machine that processes as much hay as possible. So let's say I try to, in my model, slurp up as many bits as possible and build something like a generative model that's trying to model all of the bits all at once. Well, if I make the machine, it might be able to capture some things. Let's say I make it bigger. Now it captures a larger region of the space. And obviously, as I capture more and more of the space, the likelihood that I've captured the relevant bits goes up and up and up, right? If I can model all 303 bits, obviously I can model the 3 salient bits, the 3 image bits. But I argue that this kind of strategy of just sort of throwing generative models at data is not going to get us to the place that we want to be, because real data sets have tremendous entropies because noise is cheap. It is easy to generate entropy. And just as sort of like a back of the envelope type calculation or whatever of this, entropy is it's a concept from physics, and you can normally, entropies are measured in things like energy and stuff, but we can transform this into statements about bits. And so I can ask a very specific question. Like, let's say I make some tea and I get some water and I warm up a teacup's worth of water in my tea kettle from room temperature to boiling. As a thermodynamic process, I'm injecting heat. That heat corresponds to a certain energy, and I could transform that energy into bits. And what I can actually tell you is, in terms of the number of possible states that the water in my cup could be in, if I warm it up from room temperature to tea temperature, I am kind of creating 10 to the 25 bits in the world. There are 10 to the 25 possible futures that could be explored when I do that process, and my cup is in one of them. I've created potentially a tremendous amount of information just by heating up my cup. 10 to the 25 bits. This is 1,000 zettabytes. And when you try to look up order of magnitude estimates for how much data humans have ever generated in any machine or internet or disk or drive or whatever, this is 1,000 times all the data that humans have ever generated just in warming up my cup of tea. To give another kind of scale of things, right? The Earth is in the, we're bathed in sunlight. Sunlight is a source of heat, source of power. How much information is sort of being created every second? How many possible futures are we, selecting between? The answer, that's 10 to the 38 bits per second. The world is a complicated place. I guess that's all I'm trying to say. The world is a complicated place. It's very easy to generate possible futures.
Sorry, can I
And
can I ask a question to try to make what you just said more precise about for me? So, okay, I guess what I'm trying to understand is you're saying I start with a cold cup of tea. That cup of
Yes.
tea has some distribution over states, where states here are just like the positions and velocities of all the molecules, and
Yep.
there's some like entropy to that distribution. And then you're saying that I'm going to heat it, and that's gonna then I can use like dq divided by temperature or whatever to get this like entropy.
Yep.
And so now you're saying that the number of possible, or the entropy of that distribution has increased by 10 to the 25 bits. So the two distributions that I'm comparing are the distribution of like the hot cup of coffee and the cold cup of coffee. Is that?
Yeah, the ensemble corresponding to hot cups of coffee, occupies a larger region in phase space, and the magnitude of that increase in phase space volume corresponds to 10 to the 25 bits of kind of additional phase space. So to identify, it is 10 to the 25 times harder to distinguish a particular state of the hot cup than it is to distinguish a particular state, the cold cup.
Okay.
And I mean, you never want to do that. You don't actually care
Sure,
about
yeah.
all positions and momentas, but that's sort of my point. Is it is very easy to create it's very easy to create noise. It's very easy to create entropy. It's, heating a cup of coffee creates 10 to the 25 bits in the world. None of those bits are bits you care about, but they're there.
Right.
And if
Okay,
if our way of trying to do machine learning is just to build more and more powerful generative models, that generative model has to model those 10 to the 25 bits. If it's just non-discerning, if it's just trying to model the data, that is all in there. It is harder to model hot cups of coffee than it is to model cold cups of coffee. Maybe I should put it that way.
Okay,
It's
so
much harder.
this is like reminding me of something that I never understood when I took thermodynamics. And so, okay, let's just say that I could tell you exactly the state of that cold coffee cup. That maps exactly to one particular state of the hot coffee cup. Is that right?
If you knew the process, if you could model the heating of the coffee process exactly.
So is the assumption we're making in this case that you cannot do that? Is that where the extra 10 to the 25 comes from?
Yes, in the sense that there are the phase space grows by a factor of 10 to the 25 larger amongst things that you kind of don't choose, that you don't distinguish between if all you observe is the temperature. Maybe that's the thing. Yeah. Okay. Instead, I personally think that we should look for principles that kind of try to do this. They don't just try to slurp in all the hay. They don't try to eat the whole haystack and choke on the needle. They instead look for the needle, and they try to pick out the relevant bits. Okay. Humans seem to do this. There's this paper I really like by Thomas Landauer, not the physics Landauer, but the psychologist Landauer. How much do people remember some estimates in the quantity of learned information in long-term memory? It's a really cool little experiment. He'd bring people into the room. He would show them, he's summarizing his experiment and others, bring people into the room, show them like a picture, and then send them out of the room, bring them back after some amount of time, show them a picture and ask them, did I show you this picture before? And doing that a lot of time, and with a simple sort of model that, let's assume human memory works almost like a Bloom filter, where what people do is when they look at a picture, they kind of take a snapshot, they save that binary string in their head, they, XOR it, or they AND it with their Bloom filter, and then, deciding whether or not they've seen the picture before is a measure of the error in this process. Can give you an estimate for how much information people are storing in their head. And what they discover is whether it's pictures or visual words or auditory words or sentences or nonsense symbols or music segments, if I show you a picture and you leave the room, how much are you leaving with in your head? The answer is about 11 bits. That's sort of all that you extract from that picture. Even though that picture, right, with the best sort of lossless compression schemes that we have is going to be several megabits of information. It's all there. Lots of entropy there. There's lots of pixel values. Your head, you only walk away with sort of 11 bits. You only ask 11 questions about what state that picture is in before you leave the room. And that's the kind of thing that I would like from our machine learning systems. Things that only extract dozens of bits from rich sources, but somehow make those 11 bits very salient and impressive. Okay. So how do we do this? And one thing I want to say is, like, you can actually recreate, I think, a wide array, most machine learning objectives that people train from a sort of simple like recipe. And the recipe is as follows. You describe the world the way that it exists and like the pieces that you're willing to build, the machines that you're willing to build. You sort of describe the real world on the one hand. Then you set as a target, you describe the way you wish the world would look like, the sort of target, what your desiderata are, what your dream world would look like, what success looks like, what you are shooting for. You then take the KL divergence between these two, which is the same as saying you'd wish, try to make the real world look as much as possible like the world that you desire, right? We've motivated KL divergence as an expected weight of evidence. You want to make it hard to distinguish between reality and your dreams. And then just kind of take that KL divergence, separate it into pieces, sprinkle in some coefficients to deal with modeling uncertainties, and call that your objective. And it turns out this process can generate VAEs, VIB, Bayesian inference, semi-supervised VAEs, Bayesian neural networks. All of these things are sort of just instances of this program. So let's do that. Well, let's start with the simplest case. Let's say all I was doing was generative modeling. How should we do generative modeling? And first, I want to convince you that if you follow this recipe, you'll get what we actually get, what we have. You describe the world the way it exists, and in the real world, there's some data. Data comes from some distribution P of X. And I don't know what that is, but I know that it exists, right? There's a thing that produces my data. What do I wish it looked like? I wish it came from my machine. I wish I build a model, some Q of X, and I wish the data came from that. I take the KL divergence between these. I take the KL divergence between the real world, the world that I observe, the thing that I can take expectations with respect to, and I compute the KL divergence with respect to my model, the thing that I wish were true or I wish the data came from. And this becomes your objective. You optimize this, separate into different terms, and you kind of just do gradient descent. In this case, minimizing the KL divergence between the real world and your model, you pull it into pieces, you pull apart the pieces, you get one part, which is the entropy of the true world. That's something outside of my control. I don't get to set that. The world sets that. I don't set that. And the other thing is just the cross entropy. And so the statement of minimizing the KL divergence means maximizing or minimizing the cross entropy, depending on how you put your sign in cross entropy. And that's exactly what most people do, right? In fact, most people go one step further and they, you can't actually take expectations. You don't have infinite data. And so you replace the true distribution by the empirical distribution. And what you actually optimize is the empirical cross entropy. And that is most of, to 0th order, that is what machine learning is. Maximum likelihood optimization. That's how we train most of our models. You're muted, Jonas. I think.
Why the forward scale and not the backward scale between real and world?
Because the KL is just like our M&M bags. It's the expected weight of evidence if you were to draw samples from one of them. And when you train your model, do you draw samples from your model and and ask reality what likelihood they assign to it? No. You draw data from reality and you ask your model what likelihood it assigns to it. The process is asymmetric, and it's asymmetric sort of by, I don't have control over that, right? I have to draw samples from the real world, and I can't evaluate the likelihood the real world assigns to it. But the nice thing about the KL divergence is it sort of separates. I can take expectations with respect to P. I can't evaluate the log P, but I don't need the log P because that's a constant with respect to anything I can control. It's a constant with respect to my model. And so that's, in a nutshell, most of machine learning. Let's go one step further. So let's actually make the world a little bit more complicated. Let's have 2 random variables instead of just one. Before, all we had was data X. And now let's say what I'm actually going to do in the real world is I'm going to have images X. Those come from some distribution outside of my control. And I'm going to build something in the real world. I don't just want the real world to look like my model. I want to build a thing, and let's build a representation. Let's build a machine that takes images, some neural network, and spits out a representation. It spits out a vector. I'm going to build that thing. And that thing's going to exist in the real world, and I sort of don't have to lie about that, right? At the end of the day, I'll have my machine. I'm going to use my machine as a representation. I'm going to feed images into it, and I'm going to get vectors out. So we're going to call that P of Z given X, because I'm going to imagine in the general case that my representation might be stochastic. This machine might have some noise in it or something I might want to inject as part of the process. It can or it can't, it might or it might not, but in either case, I could describe it as a conditional distribution. If it was a deterministic process, it would just be like a delta function here, but it still is a distribution, right? A density. That's a joint distribution. And as a joint distribution, I would say that describes the real world, the way the world actually exists. The real world has images and the real world has my machine. And I can send in images through my machine, and the joint distribution describing the pairs of images and representations is some P of X and Y, Z. What do I wish were true? What do I wish were the case? What's my desiderata? I really wish that my representation was sort of like, this is the normal Bayesian assumption. I wish it was a latent vector, a latent variable that could describe the images. I wish that the real world first asked my machine what the image was, it got the vector out, and then it produced the image after it observed what the representation was. I wish that were true. Right? I wish that the world followed a generative modeling assumption where first I sample representations and then I produce images in light of those representations. Because I hope that my representation is I'm looking for the needle, right? I want the salient bits. I want my representation to be something like, a green cartoon turtle sitting in the right-hand side of the picture or something. And then the process that generates images after observing my representation of it generates, this little picture. I wish that were true.
Can you say a bit
This is
more
what I
about why
have.
you wish that's true? It's not.
This is
clear.
one of a number of possible things I could wish. But all I need you to do is to agree with me that this is a wish that I could wish for.
Okay.
And I'm not unique in that wish. So, because the ingredients to our little 7-step procedure is first we describe a world that I'm sort of willing to build, and then I describe a dream that I have. And the answer that we get is going to depend on what I decide to say I'm going to build and what I set as my dream. If you change the dream, you'll change the objective, but let's stick with this dream for a second. This is a dream that all the sort of Bayesian modelers have. So we have one distribution, we have another. We want to make it as hard as possible to distinguish between these two worlds. And so what we're going to do is we're going to minimize the KL divergence. We're going to minimize the expected weight of evidence. We're going to minimize the relative entropy from the real world to the world I want. Why do we do it that way? The real world to the world I want? Because I have real images, like Jonas asked. That's what I have. I don't have sampled images. I've got real images. So I'm going to take the KL divergence, expected weight of evidence, from P to Q. This joint P, this joint Q. I'll write the joint P the way that I think about it, images, and then my representation. I write the joint Q the way that I think about it, representations, and then the image. I split this KL divergence into pieces. I get one piece, which is the expected log P of X. That's the true data entropy up to a minus sign, and that's outside of my control. It's great because I don't actually know what P of X is, but I don't need it because it's a constant with respect to my objective. And then I've got a piece which asks the likelihood that my dream generated the image that I observed after I feed it the representation that I create. This is like a reconstruction term, the likelihood of reconstructing the image. And I get this other term, which if I keep things that are like likes, I make this a ratio. The ratio of the likelihood that I generated the latent with respect to the probability that I would have synthesized the latent in my dream world. This is just taking this KL and splitting into pieces. Now, once I split it into pieces that are sort of dimensionally consistent, if I want, I can sort of sprinkle in coefficients because I might be interested in not just one solution, but a set of solutions to this problem. What are all of the different ways I could make my dream world look like the real world, where I imagine trade-offs between how close I match one term to the other. So I could sprinkle in a coefficient there, and I could imagine trading off these two terms in terms of relative magnitude. This is a beta VAE. This is the objective people train when they train a VAE, a beta VAE. It has two pieces, one of which is the distortion term. It's a measure of how likely you are, given an image, after you form the representation, then try to reconstruct the image, how likely you are to get back to where you started. And what you're trading that off with is a rate, measure of if I observe an image, I'm computing the entropy, sort of the continuous entropy. Here's a relative entropy between the likelihood that I generated the representation that I give you after I observe the image versus something that doesn't get to look at images, some quote unquote prior in the space of representations. Because that's a relative entropy between a conditional distribution and a marginal distribution, you should be suspicious that it is it turns out to be is related to mutual information, right? It's in fact a variational upper bound on what the true mutual information between the images and the representation are. I think one way to kind of think about this is once you split the thing into different pieces, you can get a geometric picture for what's going on in the objective and what you're trying to do. What you're trying to do is now you're searching in the space of all possible representations for the representations that are sort of most consistent with this worldview that your representations were the things that gave rise to the images. But when we split the objective and introduce this coefficient, we're imagining all possible trade-offs. So what you can imagine is a sort of diagram, a phase diagram, if you will. On one axis, I can measure what the distortion is. On the other axis, I can measure what the rate is. And what I mean by this is like if you give me any of these pieces, you give me an encoder, P of z given x, you give me a distribution of images, P of x, you give me some decoder, Q of x given z, and you give me some prior, Q of z. This is a number, I can compute these numbers, right? I can compute this number, the distortion, I can compute this number, a rate. You give me the 4 distributions, and I can calculate a 2-dimensional point in this space, D and R. They're both positive. R, because it's a thing that looks like a KL divergent, it has to be positive, and the distortion, if I imagine that my things are discrete, it's a probability. Probabilities are between 0 and 1, so it has to be negative of a log. It has to be positive without loss of generality. So the what I want to say is, given any of these 4 distributions, you're going to be at a single point. You might be here, you might be there, you might be here, you might be there, you might be here in the space. There's a bigger question of like which points in the space can we actually reach? Which ones are reachable, feasible, achievable? And for that, I want to take a slight detour and maybe remind you things that we talked about earlier, that we can interpret some of these KL divergence terms as if they were kind of mutual informations, basically. And in particular, both of the terms in our objective we can identify as being variational bounds on a mutual information. And I feel like I'm doing a very bad job of explaining this, but so I want to try to reset here for a little bit. But this is the term that we had in our objective. This is the rate term or the KL divergence term that you're used to seeing in a VAE. And now all I want you to kind of maybe be made aware of is that that is a variational upper bound on a mutual information. How do we show that? What is the mutual information between images and representations? How much information does the representation contain about the image? We talked about what mutual information is. And mutual information, one way to write it is as the KL divergence between the conditional distribution and the marginal. This is just a definition, right? Let's say I multiply this thing by 1. But I decide to write 1 as Q over Q. I can do that. And now once I do that, let me split this log product into 2 pieces. One of which is going to be the term that we have, this P over Q. And the other term is going to be an expected log Q over P, which is minus an expected log P over Q. That is a KL divergence. Now, I don't know what this KL divergence is. The KL divergence between the true marginal distribution of possible encodings and my made-up distribution over encodings are. I don't know what that KL is, but one thing I do know is that it's positive because it's a KL divergence. It has to be positive. And so if this term is positive, then that tells me that this thing has to be greater than this thing.
And the reason it's a minus sign is that the expectation is taken with respect to P, not Q, right?
Right, yeah. Anytime I write, and I should have said that, but in everything that follows, anytime I have the brackets just to save space, it's always with respect to the full P joint, no Qs, just to save kind of writing. Because the real world, this is kind of Jonas's point, the only thing that we're ever going to take expectations with respect to is the real world, because that's the only thing that we can kind of like, we have ready access to samples from. So all of my brackets are with respect to P, not with respect to Q. And so the KL divergence term in a VAE is itself an upper bound on what the mutual information between the input and the representation is. And so you can think about what you're doing when you kind of push on that term in a VAE is you're trying to provide a proof or a certificate or a guarantee. The lower you can make that term, the lower you can guarantee that the true amount of information retained in the representation is, because it's an upper bound. Interestingly, the other term is actually a lower bound on the same quantity. And you can see that by kind of doing the same trick again. So what we're going to do is we're going to write the mutual information again as this way. I'm going to multiply by 1, but now I'm going to write 1 as q of x given z over q of x given z. And now when I split that into pieces, I end up generating 3 pieces, one of which is the expected log likelihood of q of x given z. Another piece is the entropy of p of x, the marginal distribution over images, which again, I don't know, but as far as I'm concerned is a constant. And a term which is a KL divergence, which again, I don't know, but has to be positive. And because of the way the signs work out here, that tells us that ignoring this constant, this has to be less than this, up to a constant that I don't care about. And so what's actually happening in the sort of VAE objective is we had these 2 terms. We had a rate term or a KL term, and that is an upper bound on the actual information that we're keeping. How much noise, how much signal did we keep out of the noise, right? When we take our image and we send it through this representation, we send it through the encoder and we form a thing, there's some amount of information that's retained. The rate is an upper bound on how much information is contained. The distortion, up to a constant, is a lower bound on how much information is contained. And all we're doing when we're training the VAE is we are simultaneously pushing up on the lower bound and down on the upper bound. And the thing that controls where we end up, how much information we keep, how much we decide is signal, how much we decide is noise, where we decide to draw this wall in the, how much we assign as needle and how much is haystack, is sort of the, relatively how good we are at pushing down on one side and up on the other. And you could imagine that if I insert a beta and I kind of push harder down than I push up, I will keep less information. If I push harder up than I push down, I'll keep more information. But the VAE objective is doing this thing where it's reaching into this haystack. Your choice of beta decides how large of a ball you're going to keep. And then all you're doing is you're trying to, keep a ball of a designated size. The other thing that's interesting is once we characterize what these things are in terms of information, it also tells us, very crucially, which points in the space we can reach. Because we know that the rate is an upper bound on the mutual information. We know that the distortion up to a constant is a lower bound on the mutual information. And we sort of, this set of inequalities doesn't cover the whole quadrant, right? In certain limits, like let's say R is 0. If R is 0, I has to be 0, because I has to be positive. It's a mutual information. And so if I is 0, then D has to be greater than H. So if I restrict attention to this line, the distortion can kind of never go below the entropy. In words, what does that mean? If rate is 0, the mutual information is 0, it means I keep nothing. My encoder throws the image away and just tells you 4, right? It's a random variable. It contains no information whatsoever about the image. If I keep no information whatsoever about the image, how well can I reconstruct the image? Well, the best I could possibly do is I could generate a typical image. And there, the likelihood that I hit the right image is the log of, is the entropy. On the other extreme, if the distortion is 0, then that tells me the mutual information has to be at least H, and that tells me R has to be at least H. I sort of live over here at this point. And because of the way these inequalities are linear and stuff, I can never kind of cross this line. So in the space of all possible, you gave me these 4 distributions. It picks out a single point in the space. You can't actually reach all possible points. You can't get arbitrarily close to the origin. Just because of what we're dealing with are things like KL divergences and mutual informations, and these quantities have to be positive and related. You can't get any closer than a diagonal line where the how far out this wall is governed by a thing that we don't know, but we know is a constant, the entropy of the true data, the entropy of the images. And so for any choice of 4 distributions, you're going to be somewhere in this space, but there's sort of a line that you can't cross. The natural thing is, well, why don't we try to live on this sort of frontier, this Pareto optimal frontier? Because the ones that live on the edge of this space are in some sense optimal, right? They dominate over other ones. This point has better distortion, but the same rate as this point. So why would you ever choose this point over this point? Why would you ever choose this point over this point, right? You want to, if you want a sort of as optimal representation as possible, you want to live sort of as close to this boundary as you possibly can. Now, yeah, I sort of talked about what these things are. This point is, if you wanted to have perfect distortion, if you want to be able to perfectly reconstruct the image, then you can't throw any of the information away. And the very best that you could possibly do in terms of message link, in terms of the rate, in terms of the KL, is that your encoder has to keep all of the information. It has to keep the entropy of the images. Doing a bad job of this. Okay. If you had all of the modeling power in the world, if you really search in the space of all possible distributions, independent of any choice of model or parameters or neural networks or anything, the kind of world looks like this, with this kind of hard edge frontiers. If you restrict attention to a certain parametric family of solutions, then you can't reach all of these points. They might not all be within your parametric family. And so instead, the surface sort of relaxes to some other smooth surface that is less, there's still in the space of all possible parameter settings. Let's say each of these joint densities is represented by a neural network, and I imagine all possible settings with the parameters of the neural networks. Any setting of the parameters is going to be a point in a space. There's still going to be a set of optimal parameter settings that are a boundary or an edge in the space of all possible representations that I can form. And we want to live sort of on this edge. How do you find the edge? You would solve a constrained optimization problem. That's one way to define it, right? If I wanted to find a point on this edge, I could choose a rate, let's say this rate. And once I fix that rate, I could try to minimize the distortion. And as I try to minimize the distortion, I will eventually hit some limit, and I won't be able to get better than that. If I wanted to find some other point, I could change the rate, and I could minimize the rate, or at the fixed rate, minimize the distortion, and end up at some other point. If I wanted to describe this whole surface, I can just Lagrange multiplier. I can add a coefficient in there, and I can trace out the whole curve by varying the value of the coefficient. This is equivalent to basically like taking this picture, and you can think about beta as a angle that I rotate the space. And all I ever do is I try to find the minimum in this whole space, right? Beta equals 0 means like I rotate it by nothing. Beta equals 1 would mean I rotate it 45 degrees and I try to find the minimum. Beta of infinity means I rotate it sort of 90 degrees this way and try to find the minimum. And for any setting of beta, as I rotate this curve, I try to find the minimum point. I will kind of trace out this whole boundary. Beta equals 1 corresponds to the sort of 45 point, where if I rotate this thing 45, what's the point on this curve that has slope 45? That's what it's equivalent to. What's the point on this curve that has slope 0? What's the point on this curve that has slope infinity? And turns out this is what VAEs do. So if you train a bunch of VAEs and you kind of do beta sweeps, you end up with real solutions, and it looks like those real solutions kind of push up against what looks like a kind of wall, and they can never cross the wall. As you vary the type of architecture and you kind of lay them all on top, you end up with a whole bunch of different architectures on something like MNIST. They all seem like they sort of start lining up, and the best possible solutions all tend to agree, and they all tend to have a sort of a diagonal line that they cannot cross. And moving along this frontier has real consequences. Moving across this frontier is trading off for how much information you keep of the underlying image. And so I want to show sort of 3 examples now. If I move sort of all the way off to the side, and I just ask for the best sort of distortions I can achieve given a rate of near 0, what does it do? What does it mean? If the rate's near 0, it means that the thing keeps no information on its encoding. But if it keeps no information on its encoding, then when it tries to generate a new image, the best it can do, like we said, is to generate a typical image. And that's what this thing does. So here I'm showing if I feed this VAE these images and I ask it to reconstruct, and I'm asking it to reconstruct the same image, this 2, this 0, this 1, this 8, over and over and over again, but I'm sampling the reconstruction over and over and over again, what do I get? I just get random digits. They all look like good digits. This thing has learned a good density in the space of images, but they look nothing like the thing that I sent in. And then I can also draw, hallucinations from this model by sampling from the prior, and I'm showing what those look like here. So this model in this space lives all the way over here. You can see these sort of dashed lines. It has a rate of near 0, and all it's doing is sort of synthesizing new digits. If I try to move well over here in the space to a model that has a rate of 25 nats, I keep sort of 25 nats of information. What does this thing do? Well, now I send in this 2 and I get these 2s out. I send in a 0, I get these 0s out. I send in this 1, I get these 1s out. This 8 and get the 8s out. It's almost always the same image, right? It's keeping most of the information in the thing. It's keeping 25 nats, and it turns out the 25 nats can get you basically what I, as a human, would call a like pixel perfect representation of the image up to pixel noise, right? I feel like I'm capturing not just what type of image it is, but exactly the sort of shape of the image, except for sort of sampling noises at the edge. But then if I kind of go in between and I only keep 8 nats of information, we get something I would argue interesting, something that I would argue is approaching what we kind of set out to do, try to identify, find the needle in the haystack. This thing only keeps 8 nats of information. This thing only keeps about 11 bits. This is sort of trying to walk away from this image with the same amount of information that you as a human might walk away with. And what does it do? If I send in this 2, I get these 2s. I always get 2s, but I don't always get the same 2, right? The 2s are varying in their sort of style. Sometimes it has a loop at the bottom, sometimes it doesn't, but they're all 2s. I send in this 0 and I get 0s out. Not only are they all 0s, but they're all kind of fat 0s. So the thing has decided to keep the fact that it's a 0 and the fact that it's fat. But otherwise, at the pixel level, these things are changing a lot, right? Even at the like sort of style level, these things are changing quite a bit. You send in a slanted 1, you get slanted 1s out. They all have the sort of same slant, and they're all 1s, but they change in their shape and their thickness a little bit. I send in this 8 and I get 8s out. But again, sort of a lot of semantic variation in the types of styles of 8s that come out. These models all have the same elbow. They all have the same, roughly, the same elbow of 80 nats in this case. They're all, in terms of generative models, basically equivalent. But in terms of representations, they are very distinct. And that's maybe the point I wanted to get across. If you think about VAEs as just being a way of training a generative model, the 3 models I showed you are equivalent. Their elbow, their likelihoods are the same. But if you think in terms of representations, they're very different. They're doing something very different, and you can identify their differences. They live in different places in this space.
Alex, I had a quick question. So when we kind of choose a rate of 0, what does it mean in terms of a model? Basically, a model is kind of ignoring the input it gets and then just kind of producing some random Z. Is that what it means, like practically?
So since the rate is 0 and the rate is an upper bound on the mutual information, it means the mutual information is 0, and so that means that they're independent. And so the model, you train this VAE, you train this encoder. It's a Gaussian encoder, but if you were to actually inspect, the labels that come out are just like Gaussian random noise. It learns, it doesn't depend on the image at all. Now, and you say that, except when does this show up? This shows up if you use a powerful decoder and you train a VAE with beta equals 1. You get posterior collapse. And the posterior collapse in this geometric picture isn't necessarily like a mystery. This curve, because of the way this architecture is designed, because these models tend to have very powerful decoders, I was using a Pixel CNN decoder here, the shape of this frontier has been kind of pushed up against the wall over here. Where is the point on this frontier that has slope 1? The point on this curve that has slope 1 happens to be the left edge of this curve. When I train this VAE with beta equals 1, that's equivalent to asking which point on this curve has slope 1. Just so happens when I use a Pixel CNN decoder, because it's very good at lowering distortion relative to how good it is at modeling the rate, the beta equals 1 point lives at rate near 0. But to fix that, all I need to do was ask for a different point on the curve. All I had to do was ask for a slope that was less than 1. In this case, I think it's like 0.9
Mhm.
or something like it.
I see. So for the same given elbow, if the rate is kind of less, does it become better at generating a random kind of image? Versus if I kind of now ask it to retain some more rate, then its generation power, a typical image won't be as good. It will still be kind of close to the distribution of the image that's seen.
Yeah, so in this diagram, the elbow is the like Manhattan distance or whatever, this like 45-degree distance from the origin. Because of this family of architectures, the point that actually has technically the best elbow is also the beta equals 0 point. Basically, as a VAE, this model, in terms of like if you go to like the third decimal place, the likelihood that you achieved that was the best corresponded to the model that decided to ignore the representation. This model, yeah. But that, yeah, as a generative model, that's true. Sort of the beta equals 1 point, maybe that's another way to motivate it. It is the point that will be closest to the origin in this sense, right? Because if I had a curve anywhere,
Mhm.
and if what I'm evaluating is the sort of Manhattan distance from the origin, it's always going to be true that the slope 1 point, even if that happened to be like, over here, because the curve kind of goes like this, is going to be the point that's closest in sort of Manhattan distance to the origin. So setting beta equals 1 is trying to look for the setting of the VAE that has the best likelihood. But I guess what I'm saying is the way that we came up with the same objective wasn't as appealing to trying to train a generative model, right? What did we start with? We started with this little recipe where we wrote down the real world in which we were trying to train a representation. And we tried to make that as indistinguishable as possible from a generative model. And I guess like in terms of these actual likelihoods, I'm paying a slight cost in likelihood, but I would argue this is a much more meaningful representation of the images than the thing that spits out nonsense. Okay, that's a VAE. And hopefully you've heard about VAEs before, and now you've thought about kind of what they're doing. You can think about them in an information theoretic sense as trying to learn a representation of images. And you can think about the, beta VAE is trading off between how much of the thing it's drawing a line in the sand between signal and noise, and beta controls how large the signal region is compared to the noise. I talked about all that. What's information bottleneck? You probably heard about it, probably have less of an idea what it is. The neat thing is, because we talked about VAEs first, VIB, variational information bottleneck, is very simple. It's really just a sort of VAE, but instead of reconstructing the images, you predict labels. In terms of our recipe, how do we get there? We start with the same sort of story. There's two worlds. There's the real world and there's our desired world. But now there's 3 random variables. Because we're going to imagine what we have are images. We happen to have labels. People have gone and labeled the images with certain classes. And we're going to form representations of images. The world that we want to live in, the real world hands us pairs of images and labels from our data distribution. We don't have control over that. What I want to build is a representation, and for practical reasons, what I want to build is a representation that doesn't get to look at the label, it only looks at the image. Because at the end of the day, when I ship this thing, I'm imagining that I'm going to try to run it on images that haven't been labeled yet. So I'm going to build a representation P of z bin x that only looks at images and doesn't get to look at labels. This is the real world. I have things, and then I'm going to build a representation. Representation only looks at images. This is the joint distribution of the world I actually live in. What do I wish were true? Well, what I wish were true was that my representation captures all of the information necessary to predict the labels of the image. So I wish the world kind of looked like this. I wish that there are images and sort of independent of images. I don't care. There's representations, and that representation is in some sense a description of what the image is, and that representation is all you need to observe in order to create the label. This is what I wish were true. This is a wish I could have. If I start with this world and I start with this wish, I take the KL divergence between this and this. What do I generate? I generate information bottleneck. Take the KL, I split the terms, and I get the information bottleneck. You'll notice that this looks exactly like the VAE objective. The only difference is this used to be Q of X given Z, and now it's a Q of Y given Z. VIB is a variational classifier. It's a thing that takes an image, it encodes it with a thing that looks like a VAE encoder, And you score it based on how likely that encoding can predict the label rather than recreate the image. That's the only difference. And it has a regularization term. You can think of it as a regularization term, or you can think about it in this context as a rate, which is a variational upper bound on the mutual information. It's how much information it keeps, a measure of how much information it keeps between the representation and the thing you predict if you don't get to look at the image, right? Your marginal, quote unquote, prior. And just like in the other case, we want to insert a parameter here because we're interested in controlling or exploring the space of all possible trade-offs we could achieve between these things. There you go. That's information bottleneck, or the variational information bottleneck. It's a VAE, but you reconstruct labels instead of images. But the thoughts are all the same. We're building a representation of images that has certain properties. These things, again, you can interpret them as mutual informations. What you're doing is you're pushing down on a upper bound on the mutual information between Z and X, how much information you're going to keep about the image. You want to keep as little information as you can about the image, while simultaneously being able to predict as much information as possible about the label. That's what the objective is doing. You're pushing down on this term, you're pushing down on the information you keep, while keeping as much as possible about the label. You're looking for a compressed, a very salient, a sort of minimally sufficient representation of the images for predicting labels. Why do I think this is useful, especially in the context of classification, is because by providing a limit on the rate, on the complexity of the learned representation, you can explicitly forbid certain types of solutions. Like we all know at this point, the Zhang et al. Paper, right? Deep learning requires rethinking generalization, in which they show that if I randomly label the images, neural networks are often powerful enough that sort of without batting much of an eye, they can learn to memorize random labels relatively easily. If we think about, in an information theoretic sense, how much information does it take? Do you have to keep about an image in order to predict a random label? The answer is you need to be able to uniquely identify the image in the training set. And so if you had 60,000 images in the training set, you need to keep 11 bits in order to identify, or 11 nats, in order to identify which of the training examples it is. And then you also need to give it the label. If there's 10 possible labels, it'd be another 2.3. You would need to have 13.3 nats in order to memorize random labels. That's just you have to. No function with a mutual information, no representation with a rate less than that can memorize. And so if we are searching in the space of all possible representations that can do classification, but we're explicit about constraining the complexity of the learned representation by putting on this KL term, as long as we ensure that that KL term is less than 13.3, we can guarantee that we cannot memorize random labels. And so in so much as we still do a good job of classifying, we know that we're not memorizing the labels on the training set. We're actually learning something about the association between the labels and the images. And so, yeah, what does this actually do? So I want to give you, how does a VIB classifier compare to an ordinary classifier? To visualize this, imagine I'm doing MNIST and I send it through, I think a ConvNet in this case, in order to learn a two-dimensional representation. So I'm going to have a two-dimensional bottleneck just so I can visualize it. I take an image, I send it through a two-dimensional representation, I use the two-dimensional representation to try to predict the label. I train this thing on an MNIST training set, and then I visualize it. So now every image is a point in a two-dimensional space. And here I'm showing all of the points on the test set. And these are points. These really are points. I mean, like if you look at the floating point numbers, there's never any collisions. I checked. Every image is distinguishable from every other image on the training set because the actual two-dimensional output is distinguished, right? I had to draw finitely sized dots, so they overlap, but there's no real overlaps. If I now train a variational classifier, replace the deterministic two-dimensional encoding with something like a VAE encoder, so a thing that predicts the mean and the standard deviation of a two-dimensional Gaussian distribution. And I train that in order to try to predict. I take samples from that and try to predict the label. And I train that thing and I set the beta to be some sort of appropriate level. And what do I get? I get a thing that looks like this. Now every image is one ellipse, where the ellipse is a 1 sigma contour for the corresponding two-dimensional Gaussian distribution. And now they all overlap. This thing has thrown away a tremendous amount of information about the image. The original encoder was, for practical purposes, on the 60,000 training examples, invertible. I could, by observing the two-dimensional point, tell you exactly which training example it was. This thing is not. Take 2 of the ellipses in this sort of orange area, and they overlap almost entirely. If all you do is observe random samples coming from this encoder, you can't really tell anything except that it's over in this part of the space. And the classifier uses this part of the space to encode that it's a 1, as opposed to the other digits. The VAE classifier, by mapping the images to a two-dimensional Gaussian distribution, manages to throw away almost all of the pixels in the image, all the information in the image, except which classes it is. And so, yeah, that's what it does. Yeah.
A quick question. So how does the Gaussian representation contains less information than the point representation?
Because, so the samples from the Gaussian representation have a smaller, a finite KL divergence between that and, in this case, a trained marginal or fixed prior. So I think for this particular model, the prior was fixed to be a uniform Gaussian. Meaning if I took samples from a uniform Gaussian prior and I took samples from the encoding, you can measure the KL divergence between, the KL divergence between two joints. One joint is I take images and I encode the images and I tell you the encoding. The other joint is I take images and I randomly sample from the prior. And I give you those two sets of pairs. And I ask you how well you can distinguish between them. For this model, it has a finite degree of distinguishability. The KL divergence is finite. In this case, it's, I think, about 4 nats. There's only so much, there's a limited amount of information that the encoder retains.
I see.
While for the deterministic encoder, if I gave you those two pairs, you could sort of easily tell the difference apart because you are going to notice that every image always comes with the same representation.
I see. So in the second representation, an image is not represented by the Gaussian distribution. It's represented by a sample of that Gaussian distribution. Okay.
Yes.
Okay. Makes
Just
sense.
like for a VAE.
Okay.
Right? The encoder returns a distribution, but the way that you actually represent the image is you're drawing a sample from that distribution.
I see. Thanks.
Before you hand it to the decoder. So it turns out VIB classifiers tend to be better calibrated and stuff. I think maybe more interestingly, they give you sort of 2 measures of uncertainty because there's actually like 2 terms in the objective, and you can look at each of these terms independently. So there's a term here which kind of measures your label reconstruction, how well you can actually make a prediction, and the model can then tell you how confident it is in the prediction that it's making. But independent of that, you can look at this rate term, which is a measure of how much information it retains about the individual image. And this turns out to be a measure of almost like a wackadoo-ness, like a strangeness of the encoding sample. And I realized, sorry, I wasn't paying attention to time. I realized we're sort of up for time. People can feel free to go. I'm probably gonna to ramble for a few more minutes if that's okay. I probably just want to finish this kind of visual example and then we can chat or I can finish or anything. Okay, so to kind of demonstrate this kind of visually. Fashion MNIST is like MNIST, but it's closed. So it's 10 categories, 28 by 28 grayscale images. And here's sample images from Fashion MNIST if you haven't seen them before. What you can do is you can then ask, this model, it has these 2 measures of uncertainty. You can ask like, what are some of the high confidence mislabelings that the model makes? And the way that I'm visualizing this is that they're originally grayscale images, but I'm using color, both foreground and background, to tell you 2 different kinds of information. The foreground color is a measure of what the model thinks the class is, where it's averaging the colors of the corresponding labels. The background color is the labeled color for the image. I think that's how it goes. And basically, this VIB classifier, even the mistakes it's making on the test set are arguably correct because the model is colored green, so it says that that's a dress, but turns out in the real data set, this thing is labeled a t-shirt. And I think it's probably a dress. It doesn't look like a t-shirt to me. This thing, the model says it's a sneaker, but the data set says it's a boot. With these 2 different signals, we can actually look at 2 different kinds of things. So what we can do is we can look at samples that the model has low confidence in its prediction for versus things that it has high confidence in its prediction for. And now the overall opacity of the image, I'm encoding the kind of wackadoodness of the corresponding sample, its rate. The low confidence predictions it makes turns out to be things that don't look like the rest of the data set. I mean, most of the data set's supposed to be closed, but a few people manage to make their way in there. The shoes are usually always oriented to the left, except here there's some ones that weren't. So the model has low confidence in predicting which of the classes these things come from. It has very high confidence in predicting which of the class these things come from. These are easy examples for it. These are hard, but it can tell you which things are easy or hard. Additionally, yeah, so these sort of examples, it has very low confidence. It doesn't know what class it is, but it also has a very high rate. So it's saying it takes a lot of information for this model to try to tell you what this thing is. And even after that, it has very little idea what it is. And these are very just strange, hard to classify examples in the data set. There's things like this, which are high confidence, high rate, meaning this thing, it is certain this is a purse, but it's also certain that this is a weird purse. This has a higher rate. It has to tell you a lot more about this image than it does about typical images of purses. And most of the purses in the data set don't have nearly as large of a hoop.
And what is confidence in this context?
So I'm trying to label this is confidence. Confidence is the likelihood of a predicted label, and then the rate is going to be the KL term. Here are things that are low confidence, low rate. So the KL term is actually small here. And so the model's trying to tell you this looks like a perfectly cromulent Fashion-MNIST sample, but I don't know what it is in terms of label. It's sort of like equally split between these things being, I think, pullovers or shirts. It's not quite sure which they are, but they look like perfectly reasonable clothes. It doesn't take a lot of information to tell you what this image is, but I'm unsure. It sort of lives at the boundary between the classes. And then there's things like this, which are high confidence, low rate. So these things are just easy examples. These are perfectly cromulent samples that it's also perfectly sure are pants and not shirts or shoes.
So Alex, quick question. I thought the rate and was kind of constant over the whole data set. Maybe I misunderstood. So
oh yes, so sorry. Yes, okay. Thank you. So while training the objective, we set an average rate. What the beta is actually setting is the expected rate over the entire data set.
Okay.
But we can also evaluate that rate per image. And when you do that, you see that not all images are created equal. And actually there are, here's actually the distributions of rates that you end up with after you sort of train this thing. So, and I used to have a better example somewhere. I think I deleted the slide here, but if you then reach in and you ask, well, I guess I was showing instances over here. If you actually ask like which things have high rate, which things have low rate, here it's the things that look muddy versus the things that look clear. The model is sort of aware of the fact that some individual examples, it has to, I mean, what you're really giving it when you set the beta term is its budget. You're giving it its information budget on the entire data set. But then the model still gets to, it doesn't have to dole that out equally per example.
I see. Okay, great.
And it requires more bits in order to try to distinguish or try to describe the more complicated examples than it does the ones that are sort of simpler or easier to encode. Okay, that's sort of probably most of what I wanted to tell you. You can keep drawing diagrams like this, and basically you can draw things that correspond to Bayesian inference. You can draw things that correspond to semi-supervised learning. At this point, I think the procedure, it really is just you draw two graphical models, you take a KL divergence between them, and you can kind of recreate most objectives in machine learning. And that's maybe what I wanted to end with, this thing about information theory and all this stuff. And thank you guys for your time, and I appreciate it. And I'm happy to answer questions and things like that. And I realize I'm over time, and thank you. And I'm sorry this was unpolished, and I meant it to be better, and it was supposed to be more coherent, but thank you for taking the time and everything.
Cool, thank you. I think it was like pretty cool. Thanks, and thanks for doing this on a short notice.
Yeah, thank you for, yeah. And like I said, in the next couple days, I only have one more problem I want to finish this solution tab for. I'll give that to the organizers, people. They'll put it online. I'll drop it in the chat. Excellent. That's all I can hope for, Jonas.
Thanks,
All right, thanks.
Thanks a lot.
Thank you so much. Thanks.
Thanks, everyone.